Hi, my name is Cody Hosterman and I'm the Technical Director at Pure Storage for our VMware Solutions Engineering team. Today what I'm going to be talking about is, NVMe Fabrics, what it is, why it matters in a VMware environment, and some of the details on how to deploy and configure it. But before we get into the what and the how to use it, let's talk about the why. I think this is one of the most important things when talking about something new, and particularly a new paradigm around storage management. So to talk about why NVMe exists, we need to start with why we needed to solve a problem. What were the problems with what we had today? And what we have today, or had yesterday rather, is of course Scuzzy. And there's two parts of this, I think. One is the one we talk about, most people talk about when we're talking about NVMe, is going to be performance. And of course, that's a huge part of this. Maybe 85-90% of the reason for NVMe. But there are other pieces around this I think that are important to at least understand, and that's around the automation and how storage is managed and provisioned in modern environments. And there were some issues with this, with Scuzzy itself too. So let's talk about the performance part of this. Well, when you're talking about Scuzzy, you're talking about serialization. You're talking about spinning disk, and Scuzzy was built for spinning disk. It was built for these things that could only go so fast. And as these drives got bigger and bigger and bigger, we didn't really say they got larger. They really got essentially denser. But they didn't get any faster. These disks can only spin so fast. So while they got bigger and bigger, they got effectively slower. IOP per gigabyte. And we did all kinds of things to get around this, striping, tiering, caching, and these led to complexity or inconsistent performance or cost or some combination of all of those or some of those. And this is where Flash came in. We're like, well, spinning disk isn't the right solution moving forward, so let's invest in Flash. Flash is much faster. It's a completely different model than spinning disk. We can get the performance that we need out of it. But the problem with it was that Scuzzy was built for spinning disk. It was not built to really take advantage of the performance of Flash. And so we came into a similar problem with Flash, is that performance density became a problem because there was a usually SAS-connected, serially attached Scuzzy, and so this old management and protocol paradigm was put on the newer technology. So we couldn't really even get the performance density out of the Flash itself. And so this still became a problem. And Scuzzy fundamentally is limited. Putting Scuzzy in front of an all-flash array is kind of like having a 100,000-person stadium with 10 entrances. Yeah, you can fill it up, but it's going to take a really long time, especially if you have a lot of people trying to come in at once. It's going to be a problem. You're going to get long lines. People are going to be waiting. And it's very similar when it comes to I/O and Scuzzy. Scuzzy is a very serialized framework for managing storage and writing I/O. Those queue limits are very low, 32, 64. Not what NVMe and really what Flash can offer up. And so getting really high levels of throughput, in particular performance density, is not well married with Scuzzy. And so you have to put a lot of effort into tuning and understanding performance to be able to get close to that, or at the very least, very complicated architectures to work around it. NVMe was built for Flash. Right? Like the Pure Storage Flash Array was built for Flash, NVMe was built for managing Flash itself. This is why when most folks build computers and putting in Flash, they don't put them into some SSD drive connected via SAS. It's NVMe attached directly to the motherboard. Right? That NVMe connection and management is really where the performance comes from, or really is how it unlocks the performance from that Flash itself. NVMe was designed for Flash to take advantage of that possible performance density. And this is why it's particularly important. Furthermore, Scuzzy is very static. It was built for this. It was built for things that get plugged together. They don't really change. The interactions around adding storage, increasing capacity, adding new volumes was not really a thing when Scuzzy was built. These things didn't change very often, and so it was added after the fact. And it was frankly not well supported. There are unit attentions where you can alert on this stuff, but a lot of OSs just simply don't understand how to use that or don't use it very well. And so you still have to do that Scuzzy bus rescan every time there's new storage. NVMe was specifically built and designed to not require this. There are basic communication mechanisms between the storage and the host to understand changes in the storage capacity, geometry, and topology. Asynchronous events is what they call them inside of NVMe to say, hey, something's changed. I have new storage. I have new capacity. And so the host is alerted immediately. This really makes this interaction a basic part of how NVMe works and is what hosts and storage arrays need to support in order to get anywhere with NVMe. And so this is an important part of improving the communication too, not just the performance. And this is why we've invested in it for so long at Pure. We started many years ago with converting our NVRAM to NVMe communication. Then, of course, our internal flash, we removed the SAS SSD layer internally, and now it's connected via NVMe directly inside of our chassis. And then the expansion shelves were expanded to with NVMe via NVMe over Fabrics to our expansion shelves. And then finally, of course, opening up that stadium and attaching NVMe over Fabrics. So having NVMe in front of an all-flash array as compared to that Spaceball Stadium we talked about before is like every seat having its own entrance. If you need a lot of performance, you can do that. It can manage it, and it does not require tweaking or tuning. It's fundamentally built to support that type of performance. But of course, storage features are not built in a bubble, right? Just if your storage platform supports it but nothing else does it even matter? Well, the answer is really no. And early on with NVMe over Fabrics, or even not that long ago, really the only OS that supported it was Linux. And really, we're talking bare metal Linux here, which it exists. There's certainly a lot of it out there, but not nearly what there is around the ESX hypervisor. And so getting NVMe over Fabrics supported in the ESX hypervisor was particularly important. So in vSphere 7, VMware introduced support for NVMe over Fabrics in two modes, Fibre Channel and RoCE, Remote Direct Memory Access, RDMA, which is the Ethernet-based version of this. So this really opened up NVMe Fabrics across the industry for folks to start using it in their infrastructures because VMware is one of the most common on-premises infrastructures there is. And so getting support into vSphere was particularly important. So let's talk about some terminology. And this isn't necessarily specific to vSphere, but this, of course, matters when you're talking about NVMe Fabrics and ESX. So first off, there's the NVMe Adapter. The NVMe Adapter is what discovers and presents the NVMe storage layer inside of VMware. This is where you see your NVMe storage devices. This is what discovers it and understands how to manage that and translate it back to the VMware layer. Then there's a controller. This is not really your storage controller as you might think it. This is essentially a port. This is some target where you identify NVMe storage from. So your NVMe Adapter looks at each controller, it communicates with each controller, and that controller says, hey, I see this storage. Hey, this change has occurred. Check this out. Then there's the NQN, the NVMe Qualified Namespace. This is the initiator name. This is how the NVMe host is addressed by the target, and the target is addressed by the host. These are their NVMe unique identifiers and where storage gets provisioned and connected to. And then lastly, there's the namespace. The namespace is your volume. Maybe you would call it your LUN in the past, but this is your storage object that you format and use. You put a data store on it, you put some kind of file system. An NVMe namespace is a storage volume. So let's go into a little bit more detail on what these things are. So first off, let's talk about the NVMe adapters themselves. So in a vSphere layer, there are two versions of this. There's Fibre Channel, and then there's RoCE v2. Fibre Channel requires you to have hardware-based HBAs that support NVMe over Fabrics. A key piece here is making sure your drivers are updated, right? That you want to make sure you have your latest HBA drivers to support the NVMe over Fabrics. In some of the midterm ones, you need to enable some advanced settings to see the NVMe adapters on your Fibre Channel. So you want to make sure you have the latest, because that way you don't even need to enable things on most different HBA vendors. RoCE v2 is similar conceptually. You do need RDMA-capable physical NICs, but VMware actually offers a software version of the NVMe adapter that puts on this. There's a lot of reasons for this. One of them is the fact you don't assign IP addresses to physical HBAs in a VMware environment. You assign them to VM kernel ports. And so this is essentially what happens here is that you have an underlying NIC, You have virtual NVMe adapters that get created, and you map them to the NIC that you want it to use. And I'll walk through that process in a bit later. So within the NVMe world, as I mentioned before, there are controllers. When you click on an NVMe adapter, you can see the controllers that it sees. In a RDMA world, a Rocky v2 world, this is going to be each target port, and you'll see it differentiated on a given array by its IP address. In a Fibre Channel world, these will be differentiated by its Fibre Channel worldwide name. And so for each target worldwide name, you'll see a specific controller. And underneath each of these controllers, you'll see the storage that gets presented to it. These could be consistent across your arrays, or they might be independently managed. Of course, that's up to your storage vendor and how that gets managed. So how a host is addressed is by its NVMe Qualified name. It's NQN. Sounds very similar to iSCSI with the IQN. ESX auto-generates the NQN. There's one per host, and it's based on the host name. Today, the only way to pull this out is through the ESX CLI offering, ESX CFG or ESX CLI, and this will show you what the actual host name is and of course, what the NQN actually is. And you can predict this based on your host name and, of course, the domain name as well. If you don't have a domain name entered, it'll use the VMware one and the default VMware one instead, as you see on your screen. It will not generate this if your host is set to localhost as its host name. Don't do that. Don't do that for a million reasons. But if you do have it set, you will not see this listed. So you want to make sure your host name is set. If you do change the name, upon reboot, this NQN will also change. So there's a lot of commands, and I'm not going to spend a lot of time on these different pieces around Power CLI, or rather ESX CLI, which can be leveraged in Power CLI, around managing NVMe. And this is finding the NQN, this is identifying the controllers, this is finding the available adapters, and discovering storage as well, and seeing what you have in your NVMe environment. This is mostly beneficial because you can use this, as I mentioned, with something like Power CLI. But pretty much everything here can also be done in the vSphere client, with the exception of retrieving the NQN itself today. But I imagine that will change in the future. So let's talk a little bit about NVMe namespaces, because when you hear namespaces, it's such a different term than you're used to with Scuzzy, and also it kind of is a little bit confusing because you're the namespace, it's a unique name type of thing. What does this have to do with storage objects? So it's a little bit of a different thing. In a VMware environment, you will see a namespace available, and I'll talk about what some of these identifiers are that you see on the screen here, EUI, this crazy large LUN number. You see a namespace, and that namespace is what you then format with something like VMFS. You take that, you format it. It is physical storage, or physical in the sense that your host sees it from your array. The namespaces are your storage object. This is what you create, give it a size, you resize it, you snapshot it, you replicate it, etc., etc., etc. The namespace is your individual storage object. Now, namespaces have namespace IDs. You can view the actual namespace ID by using the ESX CLI command, and you'll see these larger namespace IDs. Now, what this is certainly varies from vendor to vendor, how it's calculated, what it starts at. And these can be very large, anywhere from 1 up to a very large number, which I'm not even going to bother going through right now, but you can see it on the screen. These uniquely identify that namespace object from that particular controller. They're not necessarily going to be unique across the earth, but they're going to be unique from that particular array. Of course, when we're talking globally, there is a namespace UUID. And this is based off of the underlying serial number of the array object of the namespace, and you can see some of these details either using the ESX CLI or, of course, even in the UI itself. VMware translates this into what is called the EUI, the Extended Unique Identifier. Looks very similar to an NAA or something like that you're used to with Scuzzy, but you'll notice this is identified via the EUI in the vSphere client, and this combines the organizational unique identifier of the vendor. It includes the identifier of the array, and then of course the specific identifier of that storage object that the array uses. Every vendor is probably going to format this slightly differently, so certainly talk to your vendor, but this is specifically what it is, the unique identifier for that namespace globally. So what about LUN IDs? Do they still exist? Well, everyone talks about hating LUNs and they shouldn't be a thing you think about, and that's really true. vVols is a similar concept as, let's not think about managing LUNs anymore. LUN IDs still exist in vVols, don't get me wrong, and they still exist in NVMe, and what they mean is a little bit different in NVMe. They, just like with vVols, they just matter a little bit less because of what they actually are. The array itself uses LUN IDs to reserve a slot to a host. A host is, here's an object that I'm provisioning storage to, and I can support so many objects presented to it or whatever. That's essentially, at least from a pure perspective, what we use our LUN ID for an NVMe namespace. You can add Scuzzy, you can add NVMe, whatever. This is how many that you can provision to this particular host. And this is, 10, 20, 254, or whatever that happens to be. Now, from a VMware perspective, there's, as I mentioned before, there's something called a namespace ID. This is a number that's based off of the serial number of the underlying array, and I'll talk of the underlying namespace itself. I'll talk a little bit more about that in a bit. The key thing here is what VMware also sees a LUN ID. It uses it to uniquely identify paths. At the end of the path, you'll see the HBA, the NVMe HBA, or virtual adapter really, the controller, the target, and then something called the LUN ID. It does not map to the array-based LUN ID at all. There is no real concept of a LUN ID within the NVMe specification. The array uses it for its own purposes, and VMware uses it because it needs something to identify paths. That's how it always works. So those two things do not map, and you should not use them to map NVMe namespaces. You shouldn't really even be using it for Scuzzy, because LUN IDs can change. They vary based on host. They vary based on day if you disconnect and reconnect. The serial number does not change. This is why we always say use the serial number to do script-based mapping, not the LUN ID, because the LUN ID only identifies a path, not an object. So what is this giant number you see in the LUN ID? Is this the namespace ID? What is this? Well, it's not quite the namespace ID, and there's a reason for this from the VMware perspective. So how we Pure generates our namespace ID is we take the last 4 bytes of the serial number, which is hexadecimal generally reported, and that is our namespace ID for that object. So the nice thing about this is no matter what host it's presented to, this volume is always going to have the same namespace ID. But you'll notice that the namespace ID is indeed seen by VMware. If you look at the black box there that's showing the ESXCLI NVMe namespace list, the number there under the namespace ID is 94,552. This is exactly what it should be from our serial number. But VMware shows a LUN ID of 94,551. One less. Why is this? Why is this different? Why don't they use our namespace ID? Well, the reason for this is that LUN IDs can be 0. Namespace IDs cannot. And so what VMware does to allow in case something needs LUN 0 is it automatically subtracts 1 from the namespace ID. That is now its LUN ID. And so if something does for some reason need 0, it is possible still with NVMe in a VMware perspective. Does it really matter for most things? No. LUN IDs don't really matter for anything these days. But this is the reason for this disparity. So let's talk briefly about vSphere multipathing. I won't go into a lot of detail here, just due to time, but a lot of the same options that you're familiar with before exist here for NVMe. The main difference is it uses a different plugin system. Previously, it used something called NMP, Native Multipathing. It has been replaced by a new high-performance plugin system. It has similar options to set up multipathing that your Scuzzy-based devices did. But instead of using something called a LUA, it uses ANA, Asymmetric Namespace Access. And this is what controls pathing and failover and so forth. VMware has its round robin and its many flavors of that, including one of the recommended ones is the one that's based on latency. Your default rules will not probably work with Scuzzy and NVMe for your array, so you need to make sure that the proper best practices are set if you're using NVMe configuration, as it may not default to what you're used to with Scuzzy, because it is using a different method with some different names, and so even setting these rules is going to be a slightly different script if you need to script it or change it or reconfigure it for NVMe compared to what you did with Scuzzy and NMP. Let's talk briefly about NVMe Fabrics with Fibre Channel. Ton of Fibre Channel out there. It's not going away. We see continued adoption around this. Now, it is losing some ground to Ethernet-based fabrics, but it's still very much a player when it comes to enterprise storage. So there's some minor differences here. You still need to do zoning. You still take your host worldwide names and your array worldwide names, and you zone them together to allow them to communicate. But what you're actually provisioning to on your array is the NQN, not the worldwide names. You're not attaching this NVMe namespace to these WWNs. You're attaching them to this NQN that is this particular host. The zoning just allows these WWNs to talk to one another via Fibre Channel. NVMe is on top of that, and what you actually provision to is that particular NQN. So this is really the main difference from an array perspective, is you don't really care about WWNs anymore. You care about NQNs. And by the way, the one thing with Fibre Channel that's not supported with Rocky today, at least as far as I'm aware, is you can boot from SAN using FC NVMe. You need to make sure you have the right HBAs and, of course, the right drivers loaded to get this done. So inside of a VMware perspective, when you configure your Fibre Channel adapter, right, you enable these NVMe-based Fibre Channel adapters, or they're enabled by default if you have the right drivers, the controllers will automatically be discovered. If you do not see any controllers, then I can almost guarantee you your zoning is not done, or you have a cabling problem or something. The communication from the host to the array is not there, so it cannot see the controllers. If you do not see any namespaces, but you do see your controllers, then you probably have not connected your namespaces to that host or not configured that host object with the NQN on the array. You have not said, hey, this NQN can see this storage on the array. Right, so when you see one of those two problems, that's generally where it's going to be. No controllers, check your zoning. No namespaces, check your array. What about Rocky v2? Rocky v2 is slightly different because there are some virtual adapters. So kind of similar to iSCSI compared to Fibre Channel is that the main difference here is that there is no switch-based connectivity that you need to configure. It's really done on the host perspective. There is no zoning with Rocky v2. The host says, yes, reach out to this target, discover from this target. Unlike Fibre Channel, we're like, all right, these particular targets on this switch can see each other, and so they all can discover one another in this particular zone. And so from a VMware perspective with Rocky v2, what you have to do is, well, you want to take your physical NICs, your RNICs, your RDMA capable NICs, add them to a vSwitch, create VM kernel adapters, and bind them, one for each RNIC you want to use. Create a software NVMe adapter for each RNIC, and then from there you can discover your controllers. So here's a bit of an eye chart, but it'll walk you through this process. First, you identify your RNICs. Yes, these ones are capable of RDMA. Add them to a vSwitch. For each one of those, create a VM kernel adapter with an IP on the correct VLAN or whatnot. Then go and add a software adapter for each one and say this software adapter directly uses this particular physical NIC. And then you want to point that to it, binding that particular VM kernel port to that NIC, and then discover the controllers from that. So this is where it's slightly different from Fibre Channel. You do need to go into the add controller and say this is my controller target, and then discover that particular controller. And this is a one-time operation in the beginning. You can do this with Fibre Channel, but Fibre Channel automatically enables this. RDMA is not going to search every IP address and tell you, oh yeah, this one has a controller and this one doesn't. This is one of the main differences between Rocky v2 and Fibre Channel. One last note on Rocky v2 is that there are some requirements on some configurations for performance on the switch, flow control, and things like that. Refer to your vendor documentation how to configure switches to make the most out of performance from Rocky v2. All right, there's some minor things I want to talk about here too, what's supported and what's not. Most of VAI is supported. The one thing that's notably missing right now is Xcopy. So that offloaded copy of VMs from one data store to another or internally to another one does not exist today. Just last year, the NVMe committee added what's called ZNS zoned namespaces extensions with simple copy. This is the Xcopy equivalent with NVMe. So it's very new. It's not yet supported by VMware. vVols is something that is also not supported yet with NVMe over Fabrics. This is still a Scuzzy thing. VMware has announced that they're working on this at the last VMworld, so stay tuned for that. Scuzzy reservations aren't supported with NVMe because they're Scuzzy. There is a such thing as NVMe reservations. So if you have hosts and applications or OSs that need reservations of something, some method or whatnot, they need to support NVMe reservation. This exists, but there's limited OS support around this, Microsoft failover clustering and so forth. RDMs are not supported today with NVMe. And of course, from a native multipathing perspective, it's been turned into the HPP. So there's nothing lost there, but it's just a new mapping. So there's still some things to work on. There's still some work to do in the VMware core storage layer. There's still some Scuzzy in there between the VM and the data store, and that's currently being worked on that's related to these other existing gaps. So if you want to find out some more information, check out our user guide on support.purestorage.com. So it'll give you information on how we implemented NVMe Fabrics, how you can use it, and of course all of our other VMware integration. You can find information around our vSphere plugin and vRealize suite and virtual volumes, site recovery manager, etc., 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 as there's a lot more going on besides just NVMe Fabrics with Pure and VMware. Thanks for your time. I appreciate it.